Hello all, welcome back to the part B of lecture 11. We will continue on logistic regression, and in logistic regression we found there are two variants of the logistic regression model. One is logistic regression with logit link, another is the logistic regression with the probit link. And what we found that we know the value of x1, x2, xp. If we can somehow estimate beta naught, beta 1, beta p, the beta coefficients, then given a x1, x2, xp, we can estimate the value of p. And that is what our final objective, that we want to estimate probability y equal to 1 or 1 minus p, which is probability y equal to 0. This is the probability that we want to estimate. So question now boils down to how we estimate beta. So what we do, we try to write the likelihood function of probit model. Suppose yi xi I equal to 1 to n contains n independent samples, and for single observation the probit model is probability yi equal to 1 given xi is phi of xi transpose beta, which is pi, and probability y equal to 0 is 1 minus phi of xi transpose beta, which is 1 minus pi. Now what is the likelihood of a single observation yi xi? The likelihood of single observation of fii xi, given there is a mistake, this given should be given xi transpose beta should be pi to the power yi and 1 minus pi to the power 1 minus yi. Now instead of pi you just plug in phi of xi transpose beta and 1 minus phi of xi transpose beta to the power 1 minus yi. And since all observations are independent, the joint likelihood of the entire sample is just product over I equal to 1 to n. So this is the likelihood function. This is the likelihood function of probit model. Now once you have the likelihood function of the probit model, you can write the log likelihood. The joint likelihood of the probit model is this. Now you can take the log of the likelihood. This will give you summation yi ln phi of xi transpose beta and 1 minus yi times ln 1 minus phi of xi transpose beta. Now once you have that, you can also write the negative log likelihood of the probit model, which is just you multiply this log likelihood function by minus 1. That will give you the negative log likelihood function. Similarly, we can define the likelihood function of logit model. Suppose yi xi is equal to 1 and it contains the n independent samples. Then for a single observation, the logit model is probability yi equal to 1 given the xi is e to the power xi transpose beta divided by 1 plus e to the power xi transpose beta, and probability yi equal to 0 given xi can be written as 1 over 1 plus e to the power xi transpose beta. Now likelihood of single observations can be written as pi to the power yi 1 minus pi to the power 1 minus yi. Now instead of pi you just plug in this functional form, and in place of 1 minus pi you plug in this functional form. That will give you the likelihood of the single observations, and then you can define the joint likelihood of as this. this product of pi to the power 1 yi times 1 minus pi to the power 1 minus yi, and where pi is e to the power xi transpose beta divided by 1 plus e to the power xi transpose beta. So now once you define the log likelihood function, you can estimate the beta through maximum likelihood estimates of beta, which is argmax of either likelihood function or log likelihood function or negative log likelihood function. Now, in order to do in most of the typical optimization subroutine, it is a minimization problem. So if you are you have to, when you are applying a optimization routine, you have to be careful whether our routine is doing it solving it as a minimization problem or a maximization problem. If it is solving it as a minimization problem, then you should try to minimize the negative log likelihood function. If it is solving as a maximization problem, then you have to solve it as a maximizing log likelihood function. Maximizing directly likelihood is bit of a questionable. Why? Because you see, if you look into it, what is pi? Pi is a probability. 1 minus pi is also probability. So these points are this is going to be a probability which is some probability between 0 and 1, and then you are taking product. So for if n is very large, then what happens for very large n, this likelihood function, value of likelihood function will start tend to 0. As n tends to infinity, become larger and large, the value of L becomes smaller and smaller. And after a while, what will happen? It will just your computer will just trunk it to 0, and that is the problem. So if you want to avoid that, so instead of working with likelihood function, it is better to work with either log likelihood function or negative log likelihood function. Gradient descent algorithm can be used to minimize the negative log likelihood function. This is general recipe for any statistical model. Remember that this is a general recipe for any statistical model. So once you have the statistical model, you write down the likelihood function, then you write down either log likelihood or negative log likelihood, then pass it to the gradient descent algorithm and try to estimate the beta. For simple linear regression, one can show OLS estimator of beta is MLE. This is I'm leaving it as an assignment. I'm leaving it as an assignment that for you guys, show that simple linear regression is OLS estimator of beta is the maximum likelihood estimator. So now in practice, you don't have to implement any optimization. There are two Python modules which implement the logistic regression. One is stats model, another is the sklearn, also known as scikit-learn. There is a built-in function called GLM in our package named stats. So in R also you don't have to worry. In Julia also there is a function called package called glm.jl. You just need to install this package glm.jl, or you can install crraw.jl. So crraw.jl also implement logistic regression with both logic and probit link. So in either you can do it in Julia or in R or in Python. All standard packages do implement logistic regression, so you can use any one of them. Thank you very much. In the next video, we will do hands-on.